Okay, so we're going to prove that if x and y are independent random variables, then the variance of x plus y equals the variance of x plus the variance of y. So let's go ahead and start this proof. So we know that the variance of x plus y is equal to the expected value of x plus y squared minus the expected value of x plus y squared, right? So now what we can do is we're going to do x plus y times x plus y, so equals. So this will be the expected value of, so this will be x squared plus 2xy plus y squared, right? If we were to do x plus y squared, that would be that. And then minus, and then we know for here the expected value of x plus y is the same thing as the expected value of x plus the expected value of y. And we don't need these two random variables to be independent for this part, right? But it will come up. So now this is equal to, so the expected value of x squared plus 2xy plus y squared is the same thing as the expected value of x squared plus 2 expected value of xy, right? Because we can separate these expected value of x squared, expected value of 2xy, and expected value of y squared. But the expected value of 2xy is the same thing as 2 times the expected value of xy. And then over here, of course, we have the expected value of y squared. And then minus the expected, so if we do expected value of x plus y squared, that'll be the expected value of x squared plus 2 expected value of x, expected value of y, and then plus expected value of y squared, right? And then this whole thing, so remember this is all of this just expanded, right? Now, I'm going to distribute that negative, right? So it'll be expected value of x squared plus 2 expected value of xy plus expected value of y squared. And then minus, expected value of x squared minus 2 expected value of x, expected value of y, and then plus expected value of y squared, right? Okay, so remember, I want to prove that the variance of x plus y is equal to the variance of x plus the variance of y. So remember that the expected value of x squared minus the expected value of x squared is variance of x, right? So I'm going to put those together. I'm going to group those. So this is the same thing as the expected value of x squared minus the expected value of x squared. So that's variance, right? I'll put another parenthesis there because that's for that whole thing. And then I can do the same thing for the expected value of y squared minus the expected value of y squared, right? And then I'm left with that plus 2 expected value of xy, and then minus 2 expected value of x, expected value of y. Okay, so now I know this right here is just variance of x, right? I know this is just variance of x, and this is just variance of y. And then I'm left with that plus 2 expected value of xy, and then minus 2 expected value of x, expected value of y. Now, remember, I know if x and y are two independent random variables, then So this is equal to the variance of x plus the variance of y. So I know if these two are independent random variables, then 2 times the expected value of xy is the same thing as 2 times the expected value of x times the expected value of y. And then that's over here, it's minus 2 expected value of x, expected value of y, right? Because if this is independent, then the expected value of xy is the expected value of x and expected value of y. So this is because these two random variables were independent. And now, of course, 2 expected value of x, expected value of y, minus 2 expected value of x, expected value of y is 0. So we're left with the variance of x plus the variance of y. So we've proven that the variance of x plus y is equal to the variance of x plus the variance of y, but only when x and y are independent, right? Because we needed that in order for these two terms to cancel. And that is the proof.